Hello, and welcome to All Space Considered, everyone. My name is Dr. David Reitzel, and All Space Considered is brought to you by the City of Los Angeles Department of Recreation and Parks, and as always, we like to thank Griffith Observatory Foundation for all the help they provide. All Space Considered is every third Thursday of the month, so we're once a month here live at Griffith Observatory. We do the show live from the Leonard Nimoy Event Horizon Theater, and you can join us, as many of the people in the audience did here tonight. We have a great crowd at Griffith, and come on up and join the show in person, or of course, you can watch it on YouTube. Tonight is Thursday, July 16th, and we have a special showcase from the AAS meeting, the American Astronomical Society meeting number 248 that we just attended in Pasadena. And we're going to have the usual suspects of the show and a little bit of a different, presented a little differently, but we've got the mostest, we've got amazing astronomical images, and we have Out to Launch, as well as science from the meeting. And then we are thrilled to have our very own plenary speaker of sorts, presenting Objects at the Edge of the Universe with Dr. Joel Leja from Penn State University, Associate Professor of Astronomy and Astrophysics. And we'll introduce him after we get our program started. Or after we do our first half of the program, I should say. This image that you're seeing in the background is actually a new artist's conception of the Milky Way. Of course, this is an initial release. We will have to see whether it holds true or not. But images, observations from the Chandra X-ray Observatory were used to look at, believe it or not, gamma ray bursts at far away galaxies. A star would burst with gamma rays, and as that traveled through the clouds in our Milky Way, it creates rings of X-rays, and you can use that geometric effect to get a distance to the clouds. And it turns out the clouds in the spiral arms of the Milky Way on the far side are further from us, as you see there, than we thought they were. So this is a new result, and we'll have to see if it is confirmed by others, but we might be a little lopsided. The Milky Way might be a little misshapen. A lot of galaxies are, so it wouldn't be that strange. Well, tonight, like I said, we are presenting from the 248th meeting of the Astronomical Society, and we were going to do the World Cup of Astronomy because, of course, the World Cup is happening. People love to call these meetings the Super Bowl of astronomy. But we thought, we don't want to have competition. We want to celebrate as much of the science as we can. And we thought, well, let's do the AAS board game, the summer edition. So here's our board game. And the first thing you have to do with any conference is your registration. You go pick up your badge. So there we are. Our Griffith Observatory token is now in the starting spot with our badge. And we'll draw our first movement card and move forward one spot. And we do that, and we land at a conference card spot. So we're going to listen to a talk. And the first one tonight is Probing Interbinary Material in a New Spider Millisecond Pulsar. Boy, that's a lot to say there, but let me explain it. It isn't that complicated. So here's the Spider Millisecond Pulsar artist's rendering. An artist drew this, but let me explain what's going on. Pulsars are formed when a star explodes. A massive star, something like 7 to 20 times the mass of the sun, so a very big star. It gets to the end of its life, explodes in a supernova, and it can leave behind a neutron star at the center. Now that neutron star is about the size of a city, about 10 kilometers across. That's about 6 miles across. This is compared to San Francisco, and they are made of nearly pure neutron material, so extremely dense. You can have 2 times the mass of our own sun in something this small, so crazy dense. Now, if they're spinning, they can be spinning very, very fast. They can shoot out beams of light along their magnetic axis. And if you happen to be lined up where that sweeps past you, you'll get a little flash of light. Now, these millisecond pulsars spin about 1,000 times a second, roughly. That's the milli part. So you'll get a little pulse of light that quickly. Now, these spider ones actually have companion stars with them, and they have a lot of hydrogen in them. The stars do. So the pulsar has its beams of light shooting out, and meanwhile, it's that energy from the pulsar smashes into the gas that's coming off of the other star, and it creates a shock wave, like you can see here, that bow, that shock wave that you can see. Now, they named them after spiders, which I don't know why, but here we go. Here's our black widow, and black widows, they claimed, had a companion star very small, probably more like a brown dwarf, something that's not quite massive enough to be doing hydrogen burning, but 3% of the mass of the sun or so. So a very small object that's having its surface blown away by the high energy from the pulsar. So about 50 of these are known in our galaxy. They also found what they called redback ones. And yes, these are related to black widows too. And these ones had small companion stars, but not tiny. So something 10 to 80% the mass of the sun. So a main sequence star. And there's about 30 of these known. And again, the pulsar is blowing material off of the star, creating a bow shock, and they're able to measure that interaction. Now the last one is the huntsman spider. They named it after, and here it comes. There's our huntsman. And the star that it's next to, that it's interacting with, is puffed up and evolved. So you can think of a red giant. A star like the sun, when it gets old, will puff up and get much, much bigger. So these are a little further away from each other. They have to have some separation. They can't be as close. And there's only 2 of these known. And this study talked about, sending the huntsman on his way, talked about making radio observations in addition to visible observations and combining these to further understand how these huntsman ones in particular interact with one another. So this was an interesting study about pulsars and their companions, which is fairly rare, but we're learning more and more about them. So time for another movement card here. We'll draw our card and we go forward 3 spots. That takes us to another conference card. So let's see what else is being talked about. The Chandra Observatory, that's in space, tracks the evolving jet from Messier 87's black hole. Well, Messier 87 is this galaxy. It's actually on our big picture. Folks here in our audience after the show, you can go out into the depths of space and see the big elliptical galaxy in the Virgo cluster. Now, this galaxy has a jet of material coming off of it. Jets can be ejected near black holes. As material falls in, it gets very, very, very hot. Some goes into the black hole, others get ejected along a narrow jet. This is an artist rendering of what's happening there. Well, this jet in M87 has been observed many years. It's been observed in the radio, it's been observed in the optical, and in the X-rays. And the X-ray observations, this is the sort of resolution we have. It looks a little blurrier than the rest. That's the telescope optics. But they were able to track the motions within this jet. And you can see up on the top is the oldest in 2012, and you can step through 2017, 2023, and finally 2025, and you can tell there have been changes in the positions along this jet. That's a little bit crazy. In astrophysics and astronomy, we usually don't get to watch changes within a galaxy. Galaxies are such big objects, things have to be moving very fast. And these jets are moving very close to the speed of light. Not quite, but they're moving very fast in order to be able to see these sorts of changes. So stay tuned for more results on X-rays and jets. So another movement card, let's go forward 6, finally a big one, although according to the game rules, we have to stop at the coffee break. Astronomers don't miss free food. We're going to go get a cup of coffee and have some snacks. So, although they've stopped giving the free food at these meetings, not anymore. There used to be. They used to have little pastries and stuff. Not so much anymore. So what do? Well, we have our coffee break, and it's sponsored by the Mostest. And Laura May, you have a good Mostest for us tonight.
Absolutely. An object we have spoken about before. And in fact, if you watched our November episode, we had Dr. Bryce Bolin as our guest to talk about interstellar comet 3I Atlas. And he was also at one of the press conferences at the AAS 248. Now, this month is actually the 1-year anniversary of our discovery of this very special comet, the 3rd ever object from another solar system passing through ours. And thanks to all the data we were able to get, we now have some theories. They're not totally proven yet, but theories as to its age, which might be very, very old, perhaps the oldest ever seen at 12 billion years old in terms of these objects visiting us in the solar system. Now, of course, we look at composition. We also look at its orbit, which is shown here as it passed through the inner solar system late last year. But it may have had a much longer journey before encountering our solar system. It might have ridden the galaxy like a carousel for billions of years. It's actually very hard to establish where it comes from because of the galactic tides that would have jiggled it up and down, but it would have formed in the disk of another forming star. Now, the galaxy has different populations of stars. We have the young disk stars, the older thick disk stars, and halo stars, which can be up to 12 billion years old. Now, Three Eyes galactic motion is a little more consistent with the Milky Way's oldest star populations rather than our younger stars, so that's pretty exciting. Now, there's still a lot of data to look at. We have another paper in the pipeline, so stay tuned for more news on this interstellar interloper.
Did they think it's part of the thick disk? Is that part of where it comes from, since
So,
it's going above and below the plane there?
I think it, certainly from its composition, from its trajectory, potentially it's from either halo stars or older thick disk. But very hard to pinpoint exactly where it comes from. But continues to be a very interesting object.
Interesting stuff. Thank you. Well, it's time for another movement card, and this time we draw so randomly, of course. One spot forward is all. We're going to go just one, and we are at an exhibit hall card. So let's draw an exhibit hall card, and it says, listen to a talk in the exhibitor theater. Move forward to the nearest conference card space. Within the exhibit hall, there are posters that are usually smaller bits of research, but there will be sometimes hundreds of those. Then there are also exhibitors. There will be telescope manufacturers. There will be observatories. There will be programs that are being run by astronomers. So you can go talk to all these folks, but lately they've also included a theater within that hall that short talks are given. And one of the committees that I'm on, the Committee for Accessibility, Rights, and Equity, gave some talks there, and they were very well attended. So people can see that sort of stuff in the exhibits as well. And so we're going to move forward to the next conference card, and we're going to pull that, and it is artificial light at night significantly degrades the value of public lands.
Yes.
Interesting.
So, show of hands here, who has seen the Milky Way before? Okay, quite a few of you.
Quite a few.
Who has seen it in a national park? Yeah, a couple of you. So that's a very valuable experience in more ways than you might think, and we can now prove it. So the AAS meeting isn't just for astronomers. There are people from other fields who come and they present research that has ties to astronomy. So in this case, we have Dr. Jordan Smith, who works in the field of tourism and outdoor recreation. Now the title of his conference, fairly straightforward. Artificial light at night significantly degrades the value of public lands, right? And this is particularly interesting because we don't often quantify the implications of a dark sky for human well-being, and very few studies have linked recreation behavior and monetary value when it comes to the dark sky. So this work was supported by the National Park Service, and they looked at a large group of national parks, which you can see right here. That's the Colorado Plateau. And they looked at this area because it has the largest concentration of dark sky designated parks in the United States. Now, one of the ways that we rate the skies is through the Bortle scale that you see here. So 1 is the darkest sky, 9 is a very light polluted sky, like Los Angeles, unfortunately. Now, a lot of atmospheric factors can affect the quality of the sky on a day-to-day basis. So here is a plot that shows the variations in artificial light through some of these parks. The full plot actually included about 36 parks over a year's time. Now the darker red, it corresponds to brighter and poorer dark skies, and some of these gaps correspond to the moon, right? When of course we have the moon illuminating the sky, and that dark line you see is the calibrated anthropogenic, that means created by humans, all-sky light ratio for each. So together they help distinguish the kind of persistent sky glow from variations that will be driven by moonlight, clouds, atmospheric attenuation. And they used visitor intercept surveys with a sample of just under 400 people, now most of whom, by the way, were unaware of the dark sky designation. And they have a good spread in terms of demographic, gender, education level, socioeconomic status, and they were able to prove that visitors are less likely to choose parks with greater anthropogenic sky glow or poorer night sky conditions, and there's a positive willingness to pay for darker skies, right? They also controlled, so you can see on this top plot on the very right at top, that's the monetary value, and they also controlled for many other factors like rain, temperature, wind speed, all sorts of things that might make you pick a park. So they also simulated small park-specific degradations to that night sky and showed that it yields substantial losses, especially in high visitation parks. So people do actually prefer darker parks, and it does motivate tourism, which related to this, we received some long-awaited news just a few days ago. regarding an application that was submitted to the FCC by a Californian startup. They have officially approved the launch of a new kind of satellite. So this is Reflect Orbital's Arendelle 1, which would use an 18 meter by 18 meter. What is that in? I'm not sure what that is in.
It's like
in feet.
Yeah, it's like 15, 16 yards.
Yeah.
Like maybe 100 hot dogs across.
Yes,
Perfect.
like that.
So they would use a mirror of about that size to reflect sunlight onto Earth's surface to create a roughly 5 kilometer to 3 mile wide beam on the ground. The image you're seeing, that is what they would like to do, right? So this is a test for the company's long-term goal. They want to deliver sunlight on demand using a constellation of tens of thousands of in-space mirrors, and they say it could power solar farms at night. But what it would also do is, of course, destroy the night sky, right? So without any respect for city, state, national borders, it could also blind people looking through telescopes. So this is an existential threat for the night sky, for astronomy, for the environment, for wildlife, for us. We know that light pollution is linked to health issues. And the FCC, they say, well, the deployment of a solar reflector is beyond the scope of what they can actually regulate. So this is basically the Death Star. I'm sorry.
It is.
I know it's a bit of a hyperbole, but that is how it can feel. And I think everyone here wants to support American technical innovation in space, but that cannot come at the cost of not only imperiling scientific research, but the entire night sky and our environment. So we'll have to see what happens here.
Yeah, one thing I want to point out, I'm going to back up to it here. With this, everybody in here has played with a flashlight, right? Your flashlight focuses, usually has a bright spot. Outside that bright spot, is there still light from your flashlight?
Yep.
Yeah. This will behave the same way. There will be a bright spot, and then outside of that will be a halo of light that isn't as bright. That's just how light works. That's how it works.
Yeah.
So no matter who these people think they are, however technical they think they are, they cannot focus it on one spot. Don't let them try and make you think that. It's impossible.
Yep.
Anyway, moving on, you can see I'm a little triggered by this.
Yeah.
Just a little. Well, you won't be able to go to national parks and see dark skies, even if you pick the darkest ones, if these things are flying around. It's just awful. Anyway, time for another movement card. Let's get back to our fun game. We're going to move forward 4 this time. Wow. Who would have known? But we end up stopping again at the coffee break. And this time our coffee break is sponsored by Amazing Astronomical Images. Ginger, what do you have for us this month?
All right, so we have some amazing images here. Love this.
Amazing Astronomical Images.
Slide
there
here.
There we go.
So starting off, we're going back for an older Hubble Space Telescope image of Centaurus A. And in this image, it reveals the lobes of jets from this active galaxy's central black hole. Now, the reason I wanted to show this one is because more recently, we have a James Webb Space Telescope image celebrating its 4th birthday of this image. And so this is a mid-infrared view of Centaurus A. Now, Centaurus A is in, of course, the constellation Centaurus. It's located about 11 million light years away, and it's a collision between 2 galaxies, usually about 2 billion years ago, so, you know, long time ago. But this key picture here that we're looking at, we are actually seeing the infrared light working here because we're able to see so much more detail. And if you actually go on the NASA website, you're able to zoom in on parts of this image, and it's just incredible how much we can see, through the dust and gases.
And if you go back and forth between the Hubble image and this one, you can see that stuff that's dark in this image is glowing in the JWST image. That's that infrared light that you're talking about.
Exactly. It's able to cut through that dense part of gas and dust. So in this next one, it's Hubble sees a swarm of galaxies. This was released on June 12th, and I just love this image, the colors in it. It kind of does look like a swarm of bees. But zoom into this, and you'll see elliptical galaxies, thin spiral lenticular galaxies, and all kinds of stuff going on in that one. Okay, now this next one, it's a Hubble image, but are we looking at a star or are we looking at a galaxy? Take a second.
Maybe both.
Maybe both.
So both. But this image actually features a dwarf irregular galaxy, and it's that little fuzzy patch that you see. So that is the actual galaxy. Wow. Now we can differentiate the stars, right, because of the diffraction spikes that you see there. But it appears so faint, and it's kind of like another little swarm of bees. Now this next one is a globular cluster. This is a Hubble image. I love globular clusters. They're one of my personal favorites. A globular cluster is actually a large, tightly bound group of very old stars, and so it's all held together by gravity. Now they called this the chandelier cluster because each one of those light bulbs is in a chandelier shape, and it's 27,000 light years away. So pretty exciting. You can also see the different colors of the stars. You have the orange ones, the blue ones. Pretty neat. All right, now, unfortunately, had to show this image. This is just 1 hour of satellites over the northern Atacama Desert in Chile, and it's a stack of a time-lapse video. So it's some of them are planes, but most of these are satellites. You also do see the lasers from the Very Large Telescope pointing up just straight up. But if you're an astrophotographer, you will understand this.
Or I think even an astronomer nowadays.
Or just someone who likes the night sky.
If things continue the way they are now, the stars will be vastly outnumbered by the satellites. So you'll go to a dark side in a national park, and even if we preserve the dark skies, you will have just satellites crawling everywhere. It won't be great.
Right, yeah. So this next one, let's see if it'll play. So this is fireworks over Los Angeles, and this was spotted by the International Space Station. So they released this video. Kind of cool. You can see all the fireworks going off.
My dog was so unhappy.
Did you see the one I made?
I
It was
did.
really cool.
I did, yeah.
But we do have fireworks in space. This is a really neat picture that I saw. This is a GK Persei in Perseus, and it is 1,500 light years away. And it was discovered in 1901, and they call it the Firework Nebula. So really neat, the colors there. And then another firework nebula. This is the Dumbbell Nebula. It's a great astrophotography target for July. So for all of my astrophotographers out there, it is located in kind of the Summer Triangle, so near, just below Vega and Altair. But it's gorgeous. So many colors in this. And another firework in space. This is the giant nebula NGC 3603, and it is part of the Carina spiral arm of our galaxy. So I just love the colors in this, and you see those stars.
I'm wearing the Jewel Box Nebula now.
Yeah, there you go. And then lastly, I wanted to show this one. This was the lunar occultation on June 17th by our famous David Pinsky. Thank you for sending this to us.
Yeah, the occultation of Venus. That's Venus.
Very hard shot to do.
Yeah.
Very
Venus
difficult.
and then
This was
the
during
waxing
the
crescent.
day. So, yeah.
Yes.
And it was during the AAS conference. We tried to shoot it outside, and this is a very, very difficult shot to do because it's so close to the sun.
Yeah.
Yeah,
So-
here on Griffith Observatory's YouTube channel, we have some footage of shots that were taken by our team here. So also be sure to check that out.
And then send us your astrophotos. Please, any astrophotography or anything of the night sky, send them to us.
Yeah, absolutely. We'd love to show off your work. Well, it is time for another movement card, and this time it is one spot. Okay, they're off. Why so small? But anyway, so we're going to move forward one, and we land on another conference talk. Let's see what it is. This time, it is diagnosing the solids in Io's volcanic plumes.
That's right, back to the lava. So if you've ever visited us at night and you've looked through our telescopes, this might be a familiar view. This is the planet Jupiter and its 4 main Galilean moons. So one of the press conferences actually focused on the innermost of these. I'm talking, of course, about Io, seen here. Looks like a big tortilla. There is science in this joke because they do have, thank you for laughing, because they do have similarities, one of which is the lack of crater, depending on your tortillas. But here is an infrared view of the moon that was captured by the Juno mission more recently. Now, all of these little hot spots you see, those are all volcanoes. So it has hundreds of them on the surface, and these were officially discovered in 1979 by Linda Morabito, not too far from here in Pasadena. through the Voyager 1 images, which she processed after these were predicted by Stanton J. Peel and his team, and which showed two active eruptive plumes. So you can see one of the ones on the limb here in that little bright spot. So this is a more modern image of Io shot in 1997 by the Galileo spacecraft with close-ups of two of these volcanic plumes that you can see here. So we've got, again, one on the limb right here and another right in the center, just left of that terminator. That's the dark line that separates the day and the night side. Now, the reddish patch you see at the bottom here, that's the shadow of that plume, which we think contains sulfur dioxide particles. Now, this moon is still very mysterious, and the volcanism on it is not driven by tectonic plates like on Earth, but by tidal heating from Jupiter's enormous gravity. So we don't fully understand why the surface doesn't have impact craters, right? We do think it's an analog of the early Earth and Moon. Possibly also some of these exoplanets, these lava worlds we might discover, and that's what makes it very, very interesting. Now, New Horizons cameras also recorded that plume that you can see here from the Tvashtar volcano. So it's about 300 kilometers or 180 miles above the moon's surface. This was in early 2007. Now, we also want to know how the plume from the volcano Prometheus has stayed active for almost 50 years across all of these missions: Voyager, Galileo, Juno. So this sequence in particular is from Voyager 2 in 1979. And so now Neil Turner's team is making a claim that there could be ash in these plumes, not just sulfur dioxide, and that the ash is covering all of these impact craters that might be on the surface. So what they did is that the researchers modeled Io's plumes with and without ash based on Galileo data. Now, ash is very important on Earth. So one of the main ways we understand volcanoes on Earth is by sampling hot lava or ash. So this is field sampling you can see here of volcanic ash from the Tajo Gaite volcano in La Palma in the Canary Islands. But what if we could do this in space? So their team is advocating for ground-based observations first to actually look at these plumes, and potentially followed by a sample return mission, which is actually much easier to do than a lander. And there have been missions proposed in the past. This was a similar concept for one that involves, you can see, flying through that kind of umbrella-shaped plume. And that might seem a little wild, but we've actually flown probes through the geyser-like jets of Saturn's moon Enceladus. And we've also brought back samples from a comet with the Stardust mission that you see here. And they would want to actually use a similar type of collector. These little cells here, they have aerogel in there. And so here are samples of dust that you can actually see. I saw them in a museum from Comet 81P or Wild 2 that were returned to us 20 years ago. Now, before flying through the plume, though, they actually suggest to have a reconnaissance pass by flying through the plume's shadow. So we can't see these from Earth on Jupiter, right? Because on Io, because it is further than us from the sun. But this is an example of an eruption on Earth, and it would help diagnose the size and potentially the type of particles in the plume as seen against sunlight. And it's safe to send the probe, and then assess if it's safe to send the probe through the plume with a collector like Stardust. So they actually modeled the brightness, you can see these three lines here, as a function of the angle that the sunlight is scattering through to reach your spacecraft's camera, depending on the size of the ash. So we would be tasting some of the material that went into Jupiter and formed the early solar system. Pretty exciting stuff. I hope this gets funded someday.
Yeah, pretty fun stuff.
Pretty fun.
And Neil, if you're watching this, hello. I was in grad school with Neil, so even on paper with him, which is fun. Time for another movement card. But do you know who painted this, by the way?
Yes, it is David Hardy. He's
Hardy.
actually painted many of these amazing astronomical vistas.
Yeah, it's I love astro art like this. It's really
beautiful.
it's inspiring. Well, time for another movement card. This time we're going forward 5 spots, but we get stopped by another coffee break because we love our coffee. So this time it is sponsored by Out to Launch.
Yeah.
Jared.
Yeah, boom
It's
coffee.
time. Let's do our countdown for Out to Launch here. So
Yeah, here we go.
We have 5, 4,
3,
3,
2,
I feel like it's slowing down.
1.
Woo! Out to launch.
Yeah.
Okay, excellent.
I gotta say, hats off to putting a sounding rocket in there, because those things they're gone. Like me after a cup of coffee,
Yep.
they're good to go. All right, so let's get this out to launch started by talking about something very exciting that happened outside of the United States. And for this, we're going to be going to China, where we have the first launch of their Long March 10B rocket. Now, their Long March 10 rocket is what they are intending on using to send humans to the moon as a part of China's lunar program. This is an entirely new rocket. China is thankfully moving away from hypergolic propellants. These are basically toxic propellants that you would allow them to touch, and then the magic happens. You know, they generate combustion, and then you get thrust out of them, but they're extremely toxic. The joke is, that somebody smelled hypergols, and they said it was like fish, but they didn't live long enough to confirm it. So they've moved away now. They're doing methalox, just like everybody is. So basically, methane or natural gas and liquid oxygen combined together. But launching just last week, everything went very, very well for their ascent. And you can notice something on the booster, the first stage, that may look a little familiar to you. Those little sort of like black squares that you see right there, those are aerodynamic grid fins. Yep, and that is because this is designed to be a partially reusable rocket. So just like a SpaceX Falcon 9 or a Blue Origin New Glenn, yes, this booster is designed to come back and land. But it does it a little bit differently. So it's with SpaceX, they could do it both on a drone ship in the ocean and on the ground. Right now, Blue Origin is doing it on a drone ship in the ocean. But in China, they're using a drone ship in the ocean, but they're not doing it fully propulsively. They have these wires right here. And these wires will actually come in and catch the booster. And this is the actual footage of that booster landing. And there are these sort of like catch hooks on the booster that catch on the wires. So they were able to successfully land their booster. Their next flight is going to refly this booster, and now China has entered the reusable vehicle club. So,
Is this more complicated to do than the chopsticks?
I think it kind of depends upon what you're trying to do. The whole chopsticks idea for SpaceX's Starship Super Heavy vehicle, which was supposed to fly today, by the way, on its 13th test flight, but they had an abort after they lit the engines, so they're going to be waiting a little while on that. The chopsticks are there for very rapid reuse, so aircraft turnaround times, if they're ever going to be able to accomplish that. This is kind of a completely different technique, and we'll have to see what it does. I guess nobody's really thought about doing it this way.
Well, it feels like they've applied aircraft carrier technology to rockets in a way.
It's like you got the three catch lines out on your carrier deck, and you're trying to hit them as best you can in your carrier airplane. So, so I guess the next Top Gun movie is going to have a Long March 10.
I think so.
I think at some point, maybe Maverick will fly a Long March 10. I don't know, but just another view of that landing. It's just really cool to me to watch these boosters come in. No word on what was burning at the inner stage at the top of that. Unsure, but hey, it's the first time, so interesting problems are expected to occur. So we will see what China decides to actually tell us. Besides, hey, we did it. So yeah.
Do they already have a date to send people to the moon for a year?
So they're looking at 2030. So which is. With the way things in Artemis have been going, specifically Starship Super Heavy being much more complicated than SpaceX expected it to be, and the new Blue Origin blowing up New Glenn rockets, we're getting down to the wire as to who is going to be returning people to the moon for Space Race Mark II, whatever you want to call it at this point. So
it was just the 4th of July, so I'll say we're going back. They're going for the first time.
Yes.
So it's
a nice way to put it. So yeah. So moving on, because I did want to talk about the last flight of this rocket right here, which is not the Lockheed 1011. or L1011 that's flying right there. Look at that.
Oh,
That is a special rocket from Northrop Grumman called the Pegasus XL. It is the only air-launched rocket in the world. It's a solid fuel rocket, and it carries payloads up to about 500 pounds into orbit around the Earth. The whole incentive is that you can fly your plane to go to your payload and then launch it from wherever you're at. And in this case, it just did its final launch, which it was launching a spacecraft for Catalyst Space on behalf of NASA called Link. This spacecraft is in orbit. It is catching up with a NASA observatory called SWIFT. And I believe it's a gamma ray observatory. And the SWIFT spacecraft did not have propellant on board. So its orbit has been dropping, and it is at risk of burning up in the Earth's atmosphere by the end of the year. So this spacecraft, Link, is actually going to go to SWIFT, dock to it, which SWIFT was not designed to be docked to, and then actually boost it using an electric thruster into an operational orbit and also control it to help out as well.
Now, my brain, of course, went to, could they be testing this to think about Hubble? Because Hubble had its last servicing mission. They don't have any more planned, and its orbit is decaying. Yet it's still functioning. The instruments are working.
Yeah, and that is definitely a valid idea. I mean, the whole idea of developing systems to have your missions go on longer is not a new one. Northrop Grumman has actually flown two what they call mission extension vehicles. These are two satellites that they have flown to geosynchronous orbit. And Intelsat, a geosynchronous satellite operator company, they actually paid to have these two mission extension vehicles basically go up to satellites that are not designed to be docked to, grab onto them, and then provide power and propulsion with that. And literally paid for 5 years of service of that. And that was done back in 2019. So, and Northrop's actually getting ready to launch another one with SpaceX in the next month. The idea of on-orbit servicing and getting your spacecraft renewed or refreshed, like taking it to get an oil change.
It's like roadside assistance.
It is.
It's orbit side.
On-orbit assistance.
On-orbit assistance.
Yeah, I'm not sure what AAA for space would be called, but that's essentially what we're watching to happen.
Very cool. Well, thank you, Jared. Fascinating stuff.
Yeah.
Appreciate it. Well, it's time for another movement card, and we go forward one space, a lot of ones in this deck, and we go forward to our final conference card here, and it is unveiling the first binary system, supernovae. Well, this image here is of the Jellyfish Nebula. Now, you might be thinking, jellyfish, I'm seeing red. Well, ignore the red cloud. Well, it's pretty. Let's not ignore it. But that's not what this story is about. You notice the glowing, sort of yellowish color glow that's in the center just to the right. It looks a little like a jellyfish with tendrils coming down off of it. There are two stars, that's the two yellowish orbs. Those we can't ignore. But then just to the left of the jellyfish, there's a little purple line, a little bit of a filament there. It's a filament of gas. And it's actually a visible part of something we call G189.6 plus 3.3. Catchy. I'm going to write a song about it later. I'm inspired.
What a delightful
Poetic.
And of course, the jellyfish is actually called IC443. Catalog numbers, folks. That's what astronomers like to use. We're boring sometimes, but it tells you where to find it in the sky. Now, they were wondering, what is that little filament? The jellyfish, we know, is actually a supernova remnant, a star that exploded in the past. But when they went and observed this region, they saw sort of that purple and green glowing area. And it was observed by collecting 16 years of data from NASA's Fermi Gamma Ray Space Telescope. And they uncovered evidence of high-impact gamma ray interactions throughout that filament's structure. So up on the top of that filament, that gas is interacting. It is shocking with another set of gas. One way you can do that is by having a supernova explosion. The star explodes, the gas moves outwards, it runs into gas in the neighborhood, and that high-speed interaction can actually create gamma rays there, especially if it's a shock from two supernovae. So we'll get to that. Indeed, big, hot, young blue stars are often found in pairs. big stars are found in binaries. They're binary fractions longer. So you would have one that's a little more massive, one that's a little less massive. And the story is the more massive one, star A, would explode first. Their lives, they sort of burn through their fuel faster, and they explode. When that happened, the companion star gets ejected. The mass that is released in the explosion is no longer there to hold on to the companion, but it has all the velocity it wants to be held by more mass. So it'll start moving outwards. Now, it moved out over time, over thousands of years, and then it exploded. Its time was up. So we're seeing one supernova explosion with another supernova explosion right on the edge of it. And that's what this is. So a pair of supernova explosions, and this is the first confirmed pair of that we've seen of this, of the remnants. So a very cool thing. And also, by the way, UV data from the Swift Observatory was used in this as well. So Swift Observatory was part of this. Our final movement card, we will move forward 4 spaces, and that takes us to the end of the conference, everybody. Now, conferences, the end sometimes just creeps up on you. You show up, you're trying to get as much info as you can, you're attending all the different talks, you're going to these coffee breaks, you're going to the panels, and all of a sudden the day's done. You think, well, I've got another 3 days. Then the next day flies by, and the next day flies by, and all of a sudden you're on the last day of the meeting, and you think, did I get as much as I could out of this meeting? And the answer is, just like all of you tonight, we can only present to you the barest amount of the science that's presented at these meetings. You can't see it all. There are talks going on at the same time. There will be sometimes 15 or 20 rooms with astronomers giving talks in them, and you have to pick and choose what you want to see, just like we picked and chose what we were going to tell you tonight here. But I recommend, if you like this stuff, go check out the press releases. You can search for AAS248 press releases. You can watch the press conferences on YouTube. You can play your own conference game, so to speak. So we hope you enjoyed this way of us putting it together, and join us, of course, in about 6 months, and we'll play the game, probably something a little different, when we review the AAS meeting from January. That one's going to be in Salt Lake City, so I don't know if we'll attend in person or if we'll just cover it from here. But we'll see you next year, everybody, for that. So thank you for our coverage.
Thank you so much.
See you next year. Bye. Going home.
And I want to thank our panel too. Thank you, Laura May. Thank you, Ginger, and thank you, Jared, for this part of the show. Yeah, thank you. Now, I'm really pleased to introduce Dr. Joel Leja from Penn State University. He's been at Penn State about 6 years. Previously, got his PhD at Yale University and was studying there. He studies objects at the edge of the universe. So we are thrilled to hear about how the James Webb Space Telescope has revolutionized this. So everybody, let's welcome Dr. Joel Leja to All Space Considered. Okay, they'll switch over, I think. Crew, tech crew, there we go.
Lovely. All right, thank you for the fantastic introduction. Thank you for the welcome, everyone. Thank you, everyone, for coming out to spend an hour and a half on a Thursday night to learn about space. One of my favorite things. So I actually grew up in California, maybe 10 hours north of here, straight up I-5. It's good to be back. And whenever I come back to California, I have a ritual. Straight to In-N-Out, one double-double, right down the gullet. All right? So maybe a normal Thursday to you all, but a big treat for me. All right, let's get started. I'm taking you somewhere a little more exotic than In-N-Out. I like to start with a little rocket launch, get everyone in the mood. So I'm going to give a brief overview of one of the most exciting mysteries from the James Webb Space Telescope. And to be clear, the James Webb Space Telescope, for people like me, hey, this is a huge deal. This is a life-defining event. It's like the pyramids, or like landing on the moon for the first time. You only get to discover the early universe once. and we happen to be doing it right now. All right, so strap in, let me tell you about it. I'll take you to the edge of the universe and we'll discuss the incredible mystery of these little red dots that James Webb has uncovered. This is the last image of James Webb as it sails off into deep space. We know it's okay, it's been operating great, so we'll come back to this later. So these little red dots that James Webb has discovered are by far the coolest and the most perplexing objects I've ever worked on. It's been a truly fantastic journey. And so much of this has been in the news already. Some of it has not. So I'll take you through it from an expert's point of view. So let's go ahead and get started. So we're going to the edge of the observable universe soon. We'll start a little closer to home. Before we start, it's important to set the vibes. So I'd like to set them appropriately with this poem by Walt Whitman. When I heard the learned astronomer, when the proofs, the figures were ranged in columns before me, when I was shown the charts and the diagrams to add, divide, and measure them, when I, sitting, heard the astronomer where he lectured with much applause in the lecture room, how soon, unaccountable, I became tired and sick, till rising and gliding out I wandered off by myself in the mystical moist night air, and from time to time looked up in perfect silence at the stars. So I say this not because I don't love charts and diagrams. I love charts and diagrams. Right? But I say it because this captures the sort of pure primal reason that many of us love astronomy. Just looking up at the stars and wondering what might be out there, what strange mysteries. And so the story I'm about to tell you, it feels a lot like this to me. Finding something in the sky that's just extraordinary, magical even, and wondering what could this possibly be. So that's the essence of where we're going to go. So vibes. Good. Before we get there, I promise I'll start a little closer to home. Good. This is Sunset, Cherry Springs Park. This is in Pennsylvania. This is one of the darkest sky sites in the eastern coast. And so you might come here to see the stars one night. You'll have a nice sunset. Maybe you'll hear birds chirping. And I know, normally I'll say, has anyone seen the Milky Way? But we've already been through that tonight. Many of you have seen the Milky Way. Congratulations. And for those who haven't, it looks something like this. The sun sets and the galaxy comes out. Absolutely glorious. A gorgeous sight. So this is the Milky Way, roughly what it looks like to the naked eye, if you're in the right spot. Not Los Angeles, sorry Los Angeles, but somewhere very, very remote. You could see the Milky Way yourself. There's a lot of glory to see, but I want to focus somewhere very special. We're going to the center. Let's not waste any time. Something that's about 26,000 light years away. Just to give you a sense of scale, if you traveled at the speed of light for all of recorded human history, before your grandparents, and so on lived, you would only be a fraction of the way there, and not a very large fraction. This is a very distant place and a very exotic place and a very strange place, as you're about to find out. So buckle in. We're headed there. We can go right there if you're feeling brave. This is a little movie courtesy of the European Southern Observatory, what such a trip might look like. So we're going to zoom right into the center of the Milky Way here, right next to the Sagittarius and Scorpius constellations. This is a very hard place to see because there are millions of suns worth of dust and gas in between us. It obscures the light. Something like 1 in 10 billion photons is lucky enough to survive the journey. But we're going to go right to the core, right to the very center. And the center of the Milky Way is an unusual place. I'll tell you why. Right now, this is what it looks like to a very powerful visible telescope. But we're going to switch on our infrared eyes. We can see a lot more detail here. So this is a picture from NASA's Spitzer Space Telescope. This is the ancient center of the galaxy. It is a strange place. There are a lot of unusual things here. It is not like home. This here, this circle, this oval, this is the nuclear stellar disk. There's 1 billion stars packed into a very dense core. And these are very old stars, 10 billion years old, 12 billion years old. This is something of a reverential place. It's been around for much, much longer than we have. So these are ancient, ancient stars. The stars here in the center of the Milky Way, they're separated by something like 0.1 light year. That's something like 42 times closer than our nearest star. There's no rest here. The night sky is very, very, very bright. This is a strange place. If you were to live here, it would feel different. We're going right into the center. We're not done zooming in. We're going to go to the heart of the Milky Way, something we call Sagittarius A star. Here, there lives something quite extraordinary. A supermassive black hole. It weighs as much as 4 million suns. So we're going to go right in here. This black hole is one of two to have the event horizon itself imaged by a telescope. This came out in 2022 from the Event Horizon telescope. This is not the picture, to be clear. There's something coming. Okay. But this is a supermassive black hole, and it's a very strange thing. And here we are. This is the picture. This is the black hole at the heart of the Milky Way, and let me just label some things for you. This here is the black hole itself. This is the event horizon. This is the point at which no light can escape. You are looking at the event horizon of a black hole, something that humans have only seen for the first time in the last 10 years, and we've only seen 2 of them, and this is one of them. You're about to see the other one too. A truly amazing thing. Why is there so much light around a black hole? This is an emission ring. This is hot gas that is swirling into the black hole, and it generates a huge amount of energy and light. It's extraordinarily bright. And we'll see a few of these in the next hour or so, 30 minutes, I won't go that long. And just to give you a sense of scale, see how big this object is, this is Mercury's orbit. This thing is big, and it is a very strange object. Why do we have a supermassive black hole at the very heart of the Milky Way? Well, we're not alone. There's at least one more out there. I'll show it to you. We actually have already had the pleasure of discussing the amazing M87 tonight. So enough with our backyard. Let's go somewhere truly exotic. We're going straight to M87. An image you've already seen today. Let me give you a bit more context for why we would go to M87 twice in one night. M87, this is our local gigantic galaxy. If you're looking for a big one, this is about as close as it gets. And it's not that close. It's 53 million light years away from Earth. So the light that we're seeing from M87 came out just about right after the dinosaurs all died. This is very ancient. And we've already talked about the radio jet emitting from the core. We're not going to talk about the jet today. We're going to talk more about the stars and the thing at the heart of M87. So the stellar body of M87 weighs as much as 400 billion suns. It's big. It is a mega galaxy. And to be clear, that's about 10 times as big as our own Milky Way. Good. The exotic center is even stranger than our own Milky Ways. It is very likely to be older than our Milky Ways, and it is something like 5 times more dense even than our own Milky Ways, which is already incredibly dense. An ancient place and a strange one. I told you we've seen 2 black holes. We've seen the one at the heart of our own Milky Way, and we've seen this one, the one at the heart of M87. This one is something like 1,000 times bigger. So even though it's very far away, we can still see it because it is so huge. This is the size of 6.5 billion suns. This is what it looks like again. And again, we see straight into the event horizon here through the power of the Event Horizon telescope. And again, we have this hot, superheated gas swirling into the black hole. And just to give you a sense of scale once more, that's Pluto's orbit. Yep. Here's the most distant thing ever sent out by mankind, Voyager 1. It would be just barely exiting the event horizon of this black hole. So you might be wondering, what the heck? Why are these things here? What is going on? Why did nature choose to put these monstrous systems at the heart of these galaxies? Does every galaxy have one? Where do they come from? Wherefore supermassive black hole? We don't know. We just don't know. We have not known for a very long time, and it bugs a lot of people. Why does nature choose to put these incredibly exotic objects at the heart of every galaxy? We do not have an answer to you. What I can tell you is that we have surveyed the local universe with some great care. And this is approximately a survey of many of the local galaxies nearby. If they're worth their salts, they often get a plot or a space on this plot. So the x-axis is, roughly speaking, how many stars are in the galaxy, specifically how many are in the core. And the y-axis is how big is the black hole that lives at the center of this galaxy. And what I want to point out to you is there's nothing down here. There's nothing down here. Galaxies and their black holes seem to know about each other. So the more stars in the center of the galaxy, the bigger the supermassive black hole. You'll see on this plot our own Milky Way, right there, down in the lower left corner. In the upper right, you could see M87, this local giant. It is not the biggest one on this plot. That belongs to NGC 1277, which has a supermassive black hole of approximately 10 to 20 billion suns worth. One of the biggest ones we know about. Why? Why do these things know about each other? Why do galaxies seem to grow with their supermassive black holes? What is going on? Again, we don't know. But we can guess. We have a few ideas. We tell some stories. Maybe they're right, maybe they're wrong. Maybe you'll know by the end of the talk. Maybe not. So, if you start at the beginning of time in some featureless hydrogen soup and you end up with some glorious galaxy like the Milky Way, full of light and order. And so on the x-axis we have our galaxy, and on the y-axis we have our massive black hole at the core. There's a few ways this could go. Maybe they grow up together. They met in kindergarten. They're best friends. They go to middle school together. They choose their college together. They grow together. They're in some sort of symbiosis. If the galaxy grows, the supermassive black hole grows. They're best buds all the way to the end. Could be. Get a little star formation, get a little supermassive black hole growth. They go hand in hand. It makes a lot of sense, actually. It doesn't have to be that way. We have also the so-called dominance track, where the supermassive black hole grows first, and the rest of us kind of grow up around it. Some sort of detritus growing around the supermassive black hole, so maybe you're here because of a supermassive black hole, the dominance story. And then, of course, we also have the adjustment story. Maybe the galaxy grows first, we form all of these beautiful stars, and then, for some reason, a supermassive black hole grows at the center. How do we tell the difference between these things? Well, you'll notice in the upper right is today, and the lower left is the beginning of time. We have to go back in time. We need some sort of time machine. Luckily, we have one. Yeah, surprise, time machines exist. They're telescopes. And the trick is, the universe is so big that light takes a very, very long time to cross it. The speed of light might feel very fast to you. You flick on a light switch, the room is full of light. On the scale of the universe, light is pretty dang slow. It takes time to get places. And so what that means is that we don't see objects in the distant universe as they are, but instead as they were. We effectively have a time machine, but only for light. So that's one trick we'll take advantage of to go back in time. If we look very far away, we're seeing back in time. It's a nice trick. The challenge with looking very far away is once you start looking really far away, like really far away, like really, really, really far away, you start running into another problem. And that is that the universe is expanding. The universe is expanding quite fast. And so that expansion will spread the wavelength of light. It will take away energy from light. And so light that is blue will turn red. Light that is red will turn into the infrared. Light that's in the infrared will turn into the mid-infrared, and so on. So we need a very special kind of telescope that can see back as far as we need to understand where these supermassive black holes come from. That is, of course, the James Webb Space Telescope. This is why it was built, or one of the reasons it was built, and one of the reasons it was designed, is to answer these kinds of questions. The James Webb Space Telescope is the most expensive telescope ever built that we know about. It cost $10 billion. It took something like 25 years to build. They started thinking about it right around the time they launched Hubble. So 1989 is when they started writing down drawings of what the James Webb Space Telescope would look like. It is a huge thing. Here, this is the Hubble Space Telescope. It's got about an 8-foot diameter mirror. I am 6'6", so it's a little bit larger than me. James Webb would be somewhere up to the ceiling from here. James Webb is gigantic. It is 22 feet tall, made of many segmented mirrors because you can't make one mirror that big. It's not very stable. This is a massive undertaking. This took the lives of thousands of scientists and engineers to put together, designed, to build, to test, to put into space. And it was designed to do this, to see within something like 200 million years right after the Big Bang. So if there's anything bright enough out there to see, the James Webb Space Telescope was built to see us. We don't really need to build anything that sees red or light. This goes out as far as we can see, approximately. The only thing farther is the cosmic microwave background, the relics from the Big Bang. So this is our chance to explore the early universe, to figure out what happened there. What are we wondering about? What are we asking? This is a little timeline of the universe. The modern universe here, all these beautiful galaxies, us. We're wanting to go all the way back to just right after the cosmic dark ages, before there were any stars. And so we built the James Webb Space Telescope to answer these big questions. Things like, how and when did the first stars form? The first galaxies? And the first supermassive black holes, where do they come from? This is what we built James Webb to answer. And so we have a lot of questions we want to ask when we built the James Webb Space Telescope. However, the way this works is that when we build these big telescopes, something funny happens. These great observatories, they work more like ships of discovery. And we're all getting on the ship, we're going over the horizon, we have some sense of what we might find there, but we don't actually know what we're going to find. And often, if we write down our 10 big questions that we want these things to answer, those 10 questions, as important as they are, they don't always end up being the most important thing the telescope discovers. This happened with the Hubble Space Telescope. And we had a list of 10 great things we wanted to learn. 30 years later, we asked, what did we learn? What were the unknown unknowns, the questions we never even thought to ask? What is the universe hiding that humans could not even conceive of when we built these telescopes? And those often turn out to be the most exciting things that these telescopes find. The stuff we weren't even creative enough to imagine before we built these things. That's why we build them. If we could imagine what the universe was like from the comfort of our bathtub, trust me, I would be doing that. Good. We have a strong tradition of pointing our biggest telescopes at blank patches of the sky and finding what might be there. So there's another quote that I just love this quote. This is from science author Nadia Drake. And this is about the first Hubble Deep Field, the first time we pointed Hubble at a blank patch of the sky. In 1995, astronomer Bob Williams wanted to point the Hubble Space Telescope at a patch of the sky filled with absolutely nothing remarkable. For 100 hours. It was a terrible idea, his colleagues told him, and a waste of valuable telescope time. People would kill for that amount of time with the sharpest tool in the shed, they said. And besides, no way would the distant galaxies Williams hoped to see be bright enough for Hubble to uncover. That turned out to be dead wrong. This is the Hubble Deep Field, that blank patch of sky. This is perhaps the most iconic image in astronomy. These are galaxies glittering like jewels spread out all across to the edge of the universe. Each of these at a different distance with a different amazing story behind it. So since Hubble, we have had this tradition of pointing at blank patches of the sky and being amazed at what's there. When Webb went up, we didn't waste any time. We went right to it. And so we immediately started doing the same game. Find somewhere completely blank and stare at it. And stare at it for a very long time. Here, this is one of these deep fields. It's very, very, very tiny on the sky. Just a tiny little patch. This one's called the Uncover Field, and some of the results I'm showing will be from this field. So when James Webb went up and first launched, we got something like this. Almost every single point of light in this image is a distant galaxy, filled with millions or billions or tens or hundreds of billions of stars. There's about 100,000 in this image alone. You can't see them all at this resolution. But to people like me who study these things, most of these are pretty run-of-the-mill. A normal spiral, a boring elliptical. What we're looking for is the tiniest little red dots. Okay, the little ones are far away. The red ones are because they've been redshifted by the expansion of the universe. And so when this telescope first turned on, there was a remarkable thing. There was a big press conference. Here was the first image release. And the funny thing is, they took all of this amazing data, and they just put it all online for anyone to use. Anyone could download it. And so people who had been sitting around and wondering and imagining and dreaming about what the early universe looked like for decades, arguing, debating, modeling, imagining, suddenly the internet has the answer to all of your questions. It's just right there. It's kind of a strange moment and kind of a magical moment, and it jumped right out at us. What's in the data? What are we going to learn? So, well, Webb started delivering immediately. Days after the first Webb data, literal days, we did not wait. We found the most distant galaxy ever seen when the universe was only 350 million years old. This is it. You'll see it looks like a little red dot, as promised. To give you a sense of scale, sharks are 450 million years old. So this galaxy is closer in time to the Big Bang, to the moment of creation, than we are to the first shark. Let that sink in. This is what we're doing here. We're probing very near the moment of creation, and it's a humbling moment. And so when you look at this little red dot and you think, geez, it's just a little dot. These photons traveled something like 13.4 billion years to reach here, and they were mostly uninterrupted on the whole way here. So these are ancient photons. Treat them with reverence. Good. This is the first record that Webb broke, to my knowledge. This record got broken again and again and again and again. Webb was built to do this, and it was very good at it. Here's one example here. This is actually a record from my research group here at Penn State. Everyone's breaking records, over and over and over. It's easy. It's all on the internet. So here, this is the second and fourth most distant galaxies ever seen by humans. Now I think they're like 5 and 7 or something like this, but they're still on Wikipedia. So here they are. Uncover Z12 and uncover Z13. Amazing. And we just kept finding these amazingly bright galaxies. And at some point, we said, wait, there are way too many of these. There should not be this many. They are so bright. They are so luminous, and we keep finding them. What is going on? This is just 300 million years after the Big Bang. This is far brighter, far earlier than anyone predicted. I'm not going to solve this mystery today. We have not solved this. These galaxies are forming in a different way than anyone expected. They call them blue monsters, even though they're red. They're actually blue. They're full of very young stars. The red is because of the redshifting of the universe. Good. Last one. Last of these record breakers. This is May 16th, 2025. This is the current record holder, MOM Z14. MOM stands for the survey name, Mirage or Miracle. Don't get any maternal attachment to this thing. This is just 280 million years after the Big Bang itself. This is our current record holder right here in all of its raw pixels. We found trace amounts of carbon and nitrogen in it. We already have heavy elements in this galaxy. This means there have been maybe a handful of generations of stars between this and the Big Bang. So again, a very humbling moment. This was supposed to be the era of the first stars, and instead we're finding galaxies full of stars. Why? What did we get wrong? What other surprises lurk at the edge of the observable universe? This is what my colleagues and I are asking ourselves all of the time nowadays, and there are dozens of theories about this. These are some of the very surprising little red dots that came from the James Webb Space Telescope. I'm going to talk about a different class of little red dots now. The story of their discovery sounds similar, but the ending is very different. James Webb was just launched. The data are just public. No one is sleeping. Everyone is doing science. Everyone is amazed at what they're seeing. So something like late at night, it was around 11 p.m., maybe a week after the first Webb data, my collaborators found some very, very disturbingly bright little red dots. They reached out to my grad student, Elijah Matthews. They said, Elijah, are you awake? Wake up, Elijah. We need you to analyze something. I think we broke the universe. Elijah's a night owl, luckily, so he had all this done by 3 a.m. And by the time I woke up at a very normal human time of 8 a.m., They had finished breaking the universe, and they consulted me, and I said, oh my God, there is something wrong here. 4 days later, we submitted this to Nature. What did we find? Why was it surprising? We found these extremely bright little red dots, which appeared to be incredibly massive, very early galaxies. We dubbed them universe breakers because they seemed to break our understanding of what was going on. Here's 7 of them. 3 of them are particularly massive. Why was this surprising to us? Well, let me give you a sense here. This is a plot of everything that came out of the first Webb data. The y-axis is how much these galaxies weigh, how much their stars weigh. This is a logarithmic scale, so each unit of 1 is a factor of 10. The x-axis is how far away they are. These are the little red dots in question. You might not be able to discern why this is amazing to us, so let me add some annotation. This is the mass of the Milky Way. This is when the universe was 3% of its current age. This was stunning. Galaxies should grow slowly. They are star factories. They work steadily for billions of years to create a stellar cornucopia, an amazing number of stars, but they're slow. They're very slow and they're very messy, and so they should not turn on so quickly. This is the equivalent of checking in on your 2-year-old and finding a 40-year-old grown-up. Right? It's very concerning. You don't know what's going on, you have questions, and you feel nervous. And that's exactly how we felt when we found these. But, you know, goes off to Nature anyway, right? And so it was under review for quite some time because the reviewers were just as puzzled as we were. But eventually they said, you know what, go for it. Why not? They seem to be little red dots. They seem to be galaxies. Let's go. That kicked off a huge media explosion. It went all over the world. This is one of the big science stories of the year, top 20. Over here was a picture of Neil deGrasse Tyson arguing with a picture of my face. Down here is a picture of me, or a video of me being interviewed on live TV, which was shocking. I was not prepared for it. They let me submit my own questions ahead of time, which I felt good about. I gave them some softballs. They got 2 or 3 questions in, and then they're like, okay, let's get to the real show. What do you think about aliens? And I was like, that's rude. NASA pays me a lot of money to not talk about aliens, okay? So anyway, we're not going to talk about aliens. People were amazed by this discovery, and so were we. They should not have been there. We got a lot more data from Webb, and we got a much better understanding of what was going on. It took some time, but this story matured, and we had a lot more facts after a while. First off, these little red dots, whatever they are everywhere. They are all over. Right? Every image from the James Webb Space Telescope contains, on average, 1 little red dot. And that is stunning because the James Webb Space Telescope surveys a very, very tiny portion of the sky. You can barely see anything. So if we find 1 for every James Webb image, that means they are all over the place. Okay? Just for reference, I did an order of magnitude calculation. If you go outside tonight and look up, you'll see something like 10 million little red dots staring right back at you. Okay? So these are super common. They are numerous. Okay? Fact 1, whatever they are everywhere. Doesn't sound like massive galaxies. Okay? 2, they seem to be pretty much unique to the early universe. However these are made, we kind of stopped making them after the first 2 or 3 billion years. It's not perfect. There might be 1 or 2 in the local universe. Studies are still going on. But they are extremely numerous at the beginning of time, and they are pretty much gone now. 2 clues. Good. All right, time to investigate. One of these things must be true. 1, we are very wrong about how galaxy formation kicks off at the beginning of time. Definitely true. 2, this is the scary thing. Our understanding of the universe as a whole, cosmology, is flawed. A lot of people said this at the beginning. None of us like to say that. Cosmology has been verified by so many branches of science in so many different ways. It's very uncomfortable to have one extraordinary thing seem to be in tension with it. That usually means you're wrong and cosmology is right. 3, another possibility. These are not galaxies at all. Maybe in the first 5 days of Webb data, we might have gotten it wrong. Instead, these are early supermassive black holes. This has its own problems, but it is a way out. What's going on? let's go back to supermassive black holes. Supermassive black holes, every galaxy has one. Remember, they're big. We see them light up when they feed on gas, on stars. They get very bright. Okay? Typically, in a normal galaxy, a supermassive black hole is about 0.1% of the mass of that galaxy. And that holds true in the Milky Way. That holds true throughout the local universe. If these things are early supermassive black holes, there is a different problem that arises from this. If these little red dots, if they work like normal supermassive black holes, which we understand fairly well, this means they are huge. They are 10% the mass of their galaxy. They are 100% the mass of their galaxy. There are many claims that these might even be naked supermassive black holes, nothing around them. This would be also huge. Our own supermassive black hole that took 13.7 billion years to form, these things would be something like 100 times more massive than our own supermassive black hole. So early. This is preposterous, right? It's almost as bad as the massive galaxies. I don't know. So, how did they get so big at the beginning of time? Were they born that way? Why? How? What did we get so wrong if these are supermassive black holes? This was like kicking a bee's nest full of astronomers. Everyone was riled up. Everyone wanted to know what was going on. And so the James Webb Space Telescope was immediately employed to get a much, much more detailed look at these galaxies. And so we got a first look at some of these early data. This is the first very, very deep spectrum that we got of these little red dots. And this was led again by my postdoc, Bingji Wang. This we thought would settle the mystery. We were absolutely sure more data would tell us conclusively. They're either gigantic galaxies or they're mega big supermassive black holes that are super early, or there's something else that we just didn't even think about, but is so obvious and so much easier to understand. And it didn't do any of those things, frustratingly. If you can't read these, let me walk you through it. Here, this is a big, bright emission line. This indicates gas spinning at thousands of miles per second. This really only happens around a supermassive black hole. So we got supermassive black holes. We're done, right? No. This is a ton of old stars. This is a thick hydrogen envelope you only see if you have tens of billions or hundreds of billions of old stars. This is a classic sign, a so-called bomber break, of a massive galaxy. So we had two extraordinary, preposterous things in our first look at this object, at these objects. Our first final discerning signature said both were true at the same time. This was very frustrating. If we were tearing our hair out before this, afterwards, I was dreaming about little red dots for a while. I don't think I've stopped. Just to give you a sense of how utterly bizarre this is. This is the equivalent of having these tiny, dense galaxies that seem to co-form with these supermassive black holes right after the universe began. What would the sky be like? What would it be like to be in one of these systems? Imagine taking our Milky Way and cramming it into a sphere 100 times smaller. And then firing off an actively feasting supermassive black hole, 100 times bigger than our own, and sticking it just 200 light years away. It's very, very uncomfortable, and no one liked this. This is Andromeda. This is a good proxy for our own Milky Way. This is what we're doing to it. We are shrinking it and keeping all of the stars and cramming them in this tiny volume. Then we're lighting off a supermassive black hole in the middle of it. This is a little red dot. This is wild even for astrophysics. This set the field on fire. No one was happy. There was a flurry of speculation. There were dozens of theories every week. Someone had a new idea, and it was even more exotic than the last. Primordial black holes formed during the Big Bang, formed in the first few seconds of the universe. Dozens of simultaneous supernovae going off. Milky Way gets about one per century, so this is a very, very strange event. Strange supermassive stars? No one quite knew. One idea, a humongous black hole eating so much gas so quickly that it looks like some sort of fast-moving atmosphere. Actually, that one's not a bad idea. Not that long ago, something like 10 months ago, the James Webb Space Telescope found two very unique little red dots, which cannot be explained by stars. These were two international teams who did independent analyses well, semi-independent, I was on both. But the conclusion of both was that these were probably something we're calling black hole stars. What is that? Is that a good name? I'm not sure still. But this seems to be the most straightforward theory, and it's not subtle at this point. But the idea is that you have a supermassive black hole that is eating so much gas, it's like a massive, thick atmospheric river, so that it looks like these old stars, and it's falling into these early supermassive black holes. That's the theory. It's a black hole star, and I'll give you a bit more of the physics in a second. This is probably the leading theory. I think the most popular theories aside from this are small perturbations on this theory. Maybe there's a little bit less gas, maybe it's in a different orientation. This seems to be the idea that people are latching onto. It could solve the biggest mystery, in my opinion, from the James Webb Space Telescope, the nature of these little red dots. But it poses so many more questions. How did these things get so big so early? Why are they everywhere in the early universe and then they seem to disappear? This is the idea of what's going on. We have a star that looks something like our sun, except much larger. And at the center, instead of fusion providing power, you have gas falling directly into a supermassive black hole. It creates a huge amount of energy. And so the black hole is here. We have a thick atmosphere. Maybe it's spherical, like a star. Maybe it's more like a puffed up disk spinning around the black hole. Maybe there's gigantic winds being blown out of the system. It's very chaotic. We don't quite know what the geometry looks like. We know there's probably a supermassive black hole and probably a lot of gas. This sounds a lot like this theory from 2008 by Professor Mitch Begelman, who predicted something called a quasi-star. And this idea is that you have a star, except at the center of the star is a black hole. Same idea. It replaces fusion. It powers the star itself. And so Mitch is suddenly feeling very nice about this. What a stunning discovery. What a great way to be verified, maybe. The jury is still out, to be clear. To give you a sense of scale, this might be something like a quasi-star, and this might be something like our sun. They are enormous. They could be up to 10 times the size of the solar system. Again, we don't quite know the size. It's a very, very large object, much, much larger than our sun and much, much larger than our inner solar system for sure. These would behave like gigantic eruptive stars. And so this gas falling into black holes, normally the signature of this is that the gas gets super hot. It's blasting out very, very hot X-rays. But these thick atmospheres of these black hole stars, they shield us. They block those X-rays. And instead, we see this far cooler type of emission. It's thousands of degrees Celsius, something like the surface of our sun. That's why we thought it was a galaxy full of stars. It seems to be like a gigantic single star, or that's the theory. Good. Black hole star, as I was just saying, it suggests a surface temperature of around 5,000 Kelvin, just like our sun. Normally these things are blasting out very, very bright X-rays, so this was also a surprise for a long time. This explains that surprise. There's no X-rays because it's shielded by a thick atmosphere. There's a way to confirm this. If you let things get just a little bit colder, around 3,000 Kelvin, not that far away, something remarkable starts to happen. You can start forming molecules, like you get in an atmosphere. N2, CO2, these things, they start to become stable. And so while we were searching for special types of giant stars in the early universe, something totally different, and we were bored of the little red dots, we didn't want to deal with it anymore. It was too weird. We wanted to do something else. Instead, we found more little red dots. And what we found in those little red dots is water vapor. A lot of it. A huge amount of water vapor in these atmospheres right here. This very characteristic boop, that is good old H2O. And so, to be clear, this paper is still under peer review, so take it with a grain of salt. But this is what we seem to find, and this water suggests that we have much cooler atmospheres than we would in a normal supermassive black hole system. And it's always fun to find water somewhere you don't expect it, especially in astronomy. So this could only really happen if the hot gas around the core black hole has been shielded by some sort of thick star-like atmosphere. We're about to wrap up here. Let me just leave you with some thoughts. The debate rages on. What are these? How did they form? Why did they form? Why did they stop forming? What do they mean? Is this the origin of the supermassive black holes we started out with? These should grow very slowly. They should eat gas over billions of years. surrounded by new stars. This doesn't seem to be what these systems are doing. Okay. What incredible physics might produce so many black holes so early from near pristine gas, from near the Big Bang, near pristine hydrogen, helium, a trace of other light elements? Do we have some direct collapse of pristine gas? Maybe the remnants of the first stars? Astronomers call this a heavy seeding event. Could be. Could it be some unknown physics producing huge primordial black holes in the first few seconds of existence? In the first few minutes of the universe? Could be. Is it some other thing? Is it some new, extraordinarily rapid form of black hole feeding during the so-called black hole star phase? Maybe every supermassive black hole goes through this phase. It's very normal. It's like going to high school. Maybe not so much, but who knows? We don't know. This is still a new class of objects. We don't get to discover a new class of objects very often. We especially don't get to discover them when they're so bright and so much all over the place. This is a truly extraordinary event. So these are early days. Webb has looked at less than 0.1% of the sky. There are far more mysteries waiting to be discovered in the deep universe. So stay tuned. Who knows what we're going to find? One last thing. I'll take you through this quickly. Let's assume there was some cosmic vending machine. You can transform money into knowledge. You go on, you put in $5, you get a secret of the universe. Another $5, another secret. Sounds fun, right? What if I told you some of these secrets were getting signals of life on planets around other stars via looking at their atmospheres, the atmospheres of exoplanets? Or seeing the birth of the first stars? Or mapping the universe out to the great impenetrable cosmic fog. You get to do those things. You put a little money in the machine, you get out a secret. How much money would you put in? $10? I'm not going to ask you for money, to be clear. But think about it. What is that worth to you? These are big questions, and you can get an answer. You just have to put a little money in the machine. Good to come up with a number. I don't know. I got lunch for like $20 this morning. $20 seems not unreasonable. Find a few secrets of the universe. Well, good news. You already put that money in. And per person, that money was $30. I hope you would value this more. But to be clear, that is how much it cost you. The James Webb Space Telescope is $30 per American. And so, as one of my colleagues, Grant Tremblay, puts it, JWST is witnessing the birth of stars until the edge of time for what U.S. consumers spend annually on potato chips. Talk about a good investment. All right, that's all. Thank you, everyone.
All right. Well, thank you so much for that. Folks, we do have time for a few questions. So does anybody in our audience have a question for our speaker? Yeah, here in the front.
So does this mean that we're going to get closer to answering the question, what came first, the supermassive black hole or the galaxy?
So are we going to be able to answer the question, what came first, the supermassive black hole or the galaxy? Probably. We still haven't fully converged on what these things are. I think they are probably supermassive black holes with a lot of gas around them. That's the most compelling evidence to me. It's the only theory that seems to go through all the data. If you are being a bit of a stickler, and there are many sticklers in astronomy because we're very skeptical scientists, you might instead stand in front of this room and say, there is no evidence that there's a supermassive black hole at all. All we see is a thick wall of gas, and we don't know what's in the core. It could be anything. It could be a black hole. It could be something totally different. I don't even know if it is feasible to peer through the core of these things and see a black hole in there. So I would like to think that this is the answer to that question, and there are very compelling arguments that suggest it might be, but the true answer is it's very hard to say, and without some brilliant idea, or perhaps many brilliant ideas, it's not even clear we're going to be able to conclusively demonstrate these are supermassive black holes. Limits of knowledge. I hope so.
Yeah, I have kind of a follow-up question to that. In the high-speed gas you showed in the peak, you said that was evidence that we needed to have a supermassive black hole. How close to the black hole does that gas need to be? It seems like if you're at a giant star, that would be hidden by the surface of the giant star.
Ah, sir, you have put your finger on the great paradox of those lines. What we first thought they were was gas moving right next to the event horizon of the black hole very fast, as you say. But if you then surround that black hole with a very thick stellar atmosphere, you would never see that gas. Right?
Yeah.
And so the theory now, and this is being debated with great vigor, are we seeing the center of the supermassive black hole somehow? Or are these broad lines not a sign of very fast spinning, but instead photons bouncing off a very thick atmosphere? That is playing out right now in the literature, and I cannot tell you who is right. I have my own opinions, but we don't know. So that is how we get out of that, and that's how that might not actually be a supermassive black hole signature, as we all originally thought it was.
So we need to wait for another press conference at the next AAS from you, perhaps. So.
Yes.
Other questions in our audience here? Let's see. Yeah, one over here.
So I'm still a little confused about the black hole star that you mentioned. I know that we don't know much about it, but how do we know it's not just like an unnaturally large star or a black hole with just a really big accretion disk? Because that's very unique.
That is a lovely question. How do we know this is a black hole star and not just a normal gigantic star? That is a scientific question, and I appreciate it. We have theories for stars that get huge. The biggest star we've seen conclusively is somewhere around 120 solar masses. People spend a lot of time building theories of how stars might get huge. 750 solar masses, even 1,000 solar masses. And we think some of the first stars might have even gotten a little bit bigger than this. These theories are pretty well developed. We understand them pretty well. You just can't power something this bright with fusion. That's what it comes down to. And so we wouldn't see a single star this bright from the edge of the universe. You might say, Joel, it's not a very satisfying answer because you made it on a computer and your computer's not the universe. And I would say that's an excellent point. I don't know. Maybe supermassive stars have some other properties, and maybe these are supermassive stars. I would be a bit surprised. But they seem to also cluster in the sky like galaxies do. So that's our other hint. But if we found out they were maybe some surprising massive type of star, I wouldn't be that shocked. There's a lot of room for crazy theories here, so astronomers love these things.
Any other? Well, let's thank our speaker again. Thank you, Joel. Absolutely fantastic. We're looking forward to future results from you. And tell us first so we can break the news. So, well, folks, thank you so much for joining us at All Space Considered tonight. As always, we had a fantastic speaker. The panel was wonderful. I want to thank them again. All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks, the City of LA, and as always, we'd like to thank Griffith Observatory Foundation, our exclusive nonprofit partner. And I'd like to thank everybody that came out to see us tonight. I'd like to thank Penn State, our speaker, and I'd like to tell you that next month we have, here we go. On next month's All Space Considered, we have Dr. Gail Schaefer from the Chara Array up at Mount Wilson. Mount Wilson is still doing groundbreaking research in astronomy, and we'll hear all about it next month at All Space Considered. So thank you for joining us tonight. We'll see you next month.